Yep. Hi everyone, I'm Ollie Dodge, a third year PhD student at the University of Manchester, supervised by Professor René Breton. Firstly, of course, big thank you to the committee for accepting my talk and me the chance to present. Also, big thank you to Marilyn for allowing me to present with a PowerPoint due to my massive over-reliance on GIFs, which we'll soon learn about. Today I'm going to be talking about optical modelling of spider pulsars and specifically how we can try and constrain pulsar masses using it. I've got a lot to get through quite quickly, so we'll get straight into it. So, starting with what are spider pulsars? Pragma kind of introduce them slightly. We'll have a deeper look here. These are pulsar binary systems consisting of a millisecond pulsar primary, or MSP for short, paired with a non or semi-degenerate low mass companion. And the pair of them are locked in tight, so sub 24-hour orbital period, tidally locked orbits, which means the pulsar wind really strongly ablates one side of the companion, but it's always facing the pulsar. This gives us one hot irradiated day side and a cold unirradiated night side. And from the day side, we expect material to be ablated and kind of follow along its orbit as a kind of cometary tail, which produces those radio eclipses Pradman introduced. I don't really care about radio eclipses. I'm more bothered about the science questions, specifically the second one. What is maximum pulsar mass? This is because a number of spider systems have shown potential to contain supermassive neutron stars, so potentially having above 2 neutron star masses, solar masses, which if we can precisely constrain the masses of these systems, it allows us to basically fit a cutoff to the observed neutron star mass distribution and say an observed maximum neutron star mass, which we can then use to constrain equations of state. So that was a weird noise. That's the very quick background. And how then do we actually constrain the masses of these systems? Well, we start from the binary mass function up in the top left, and we are aiming for MP, for pulsar mass. If we have a nice radio timing ephemeris, we get the orbital period of the system and A1, which is the distance between the pulsar and the system center of mass. Combining this with the companion's radial velocity, we can get to Q, the mass ratio, and then throwing in the orbital inclination, we get to the pulsar mass. So there's our group. So, given a orbital ephemeris, what we need is inclination and radial velocity to be constrained. And this is all possible through the power of optical modelling. And specifically, I'll start with inclination, which is done with light curve modelling. But first, what does a spider light curve actually look like? This is a pretty typical one. We see nice big sinusoidal modulation peaking once per orbital period. So this is copied for 2 periods. And this is a direct effect of that irradiation I mentioned before. So once per orbit, we see the hot day side of the companion and get an optical maximum. Once per orbit, we see the colder night side and get an optical minimum, producing this nice sinusoidal modulated at the orbital period. We can also get a bit of ellipsoidal modulation, which causes double peak light curves in some systems, which is just because the companion fills its Roche load. So we expect it to take on a kind of teardrop shape and see slightly higher surface area at these positions in the orbit. So that's what light curves look like. How then do we model them? We do this using Icarus, which is a binary light curve synthesis software, chiefly pioneered by my supervisor, Professor René Breton. And it starts from here, the gravitational equipotential equation, which defines our Roche load for the system. We then place the stellar companion in there and define its surface with a load of surface elements. We can then assign each of these a surface gravity and then a temperature, whack an irradiating temperature onto one side, which mimics the effect of that pulsar wind, and we get something resembling a spider companion. So for each of these points, we have a surface temperature, a surface gravity, and using photometric atmosphere grids, we can get the flux we expect to observe from each of these surface elements. Then it's just a case of working out which of these surface elements we can see for a given point in the orbital period, and summing these fluxes over the visible surface to construct our light curve. So spin the companion around, and the light curve just falls out. Lovely. How does this then actually constrain the inclination? Well, we need to look at the amplitude of the light curve. And this is basically just because at low inclinations, so based on orbits, always get confused, you see a mix of a day side and night side throughout the orbit, so you don't expect to see much variability. Whereas when we go to edge-on inclinations, you see the full day side and then the full night side, you get a really strong variability. variability. So that's how we get to inclination. What about the companion's radial velocity? So for this, we need to move from photometry over to spectroscopy. And just like with photometry, we expect to see quite different spectroscopy depending on whether we're looking at the day side or the night side of the companion. So hot irradiated day side, hot spectral absorption lines. So here we've got the Balmer series, all of which have fairly high activation energies, say about 7,000 Kelvin or so. Whereas towards the night side, we don't expect temperatures to reach this high. We don't expect these lines to be activated. So in terms of constraining the orbital velocity, what is typically done is basically pick a line and watch it over the orbital period. You will get a Doppler shift at its rest wavelength, and you can fit a sinusoid to the amplitude of that, and that's your radial velocity amplitude. This is typically done by cross-correlating spectral templates with phase-resolved spectroscopy, but this can be difficult for spiders because of their not only changing temperatures as a function of phase, but even if we're at this particular orbital phase, you've got one temperature on this side, one temperature on this side. One spectral template is very rarely going to fit very well. So it's quite imprecise doing this with spiders. So Icarus is trying to address this in much a similar way to simulating the photometry. We just use spectroscopic atmosphere grids, which are basically the same, just with a big wavelength axis. And again, sum the expected spectrum for each of those surface elements per orbital phase, and you get out the expected spectroscopy. And then again, model that over the orbital period, and we should get our center of mass orbital velocity. So we've got two ways we can apply this. This is kind of the main thrust of our new Icarus iteration. Depending on what we've been provided, either we have just the radial velocity curve, someone's observed some spectroscopy and got a radial velocity curve out of it. We can fit an Icarus model radial velocity curve to that observed one and use that to penalize our models, or we get this full-on spectra, we get the raw spectra, reduce it, and compare it with our Icarus model spectrum and use the residuals to penalize our models. So I've got two case studies, one for each case, starting with PSR J1910, tape 5320, forgot the 20. This is a Trapham source, so thank you Trapham collaboration for getting me onto this. And it started life, and why Colin mentioned it as a Fermi unassociated source, but since it's had me, I pointed at it, and we get a timing ephemeris. We also have some nice radial velocity curves, two in fact, and these trace different points in the spectroscopy. So remember what I said about the day side and the night side. We have a Balmer line dominated radial velocity, which tracks this part of the star, and a magnesium B triplet, which is one of those metal lines, which might track this part of the star. And we can see we get different radial velocity amplitudes depending on which we're looking at. So if we kind of look at the, I guess, geometry, maybe we expect the center of mass radial velocity to come somewhere in between the two. So even before doing the cross correlation, we could constrain the center of mass using those two, right? We applied our radial velocity modeling to this, and the answer may be no. We're finding this bracketing certainly isn't happening for 1910, or at least our modeling doesn't seem to think so. We're finding our sampled center of mass radial velocity is consistently coming in higher than the magnesium B triplet, so then that night side radial velocity. So we're moving from this sort of situation over to here, where the magnesium B triplet is still higher than the Balmer line radial velocity, but it's lower than the center of mass, which means we would expect it to be found closer to the day side of the star, which isn't the most intuitive, given that I said the magnesium B triplet should be stronger towards the night side. But if we actually model the surface of the companion, which is what I'm showing here, we have, this is mislabeled, many apologies. This should be normalized equivalent width times by the continuum of that surface element. And this is basically a proxy of the brightness of the magnesium B triplet from the surface elements on the star. And we can see it's much brighter towards the day side. If we were having this sort of situation, we'd expect it to be brighter over here. So very much not expecting this bracketing behavior here. Whether this is just something for 1910 or something that can be applied to previous sources remains to be seen. But we need to get to the bottom of this, and if we can, it should lead to some nice precise pulsar mass determinations. Then we come on to our full spectroscopy modeling. Oh no, my slide. Oh well. This is an application of our full spectral modeling. The reason for this is because of this paper, Romani 2021, which makes a really strong case for one of these supermassive neutron stars in this system. where they use a radial velocity curve and use it to penalize some of their photometry models and find consistently, thank you, pulsar masses in excess of 2 solar masses, so really big neutron star probably here. And if we think back to that initial science question, constraining the maximum neutron star mass, these are exactly the sorts of systems we want to be bringing this full spectroscopy modeling to bear on. Really high pulsar mass, so hopefully really close to the end of that maximum neutron star mass distribution, and we want to constrain that really tightly to get the best possible cutoff. So that's what we've been trying to do. We acquired their spectra and have been modeling it. Progress has been somewhat slow due to GPU-based roadblocks in my PhD, but we're getting there, and I'm coming back to kind of work on this source a lot more. Don't judge this corner plot, very, very unphysically high pulsar mass that's wanting to go even higher. But when we compare with the similar Romani models, we do find a 20% improvement in the companion radial velocity constraints, which pass down again, stinky, but 10% improvement in the pulsar mass constraint, but very preliminary, a lot more work to do on this. So a lot of watch this space in this talk, but it does seem to be going somewhere. So in conclusion, I hope I've convinced you that optical modeling of spiders is a good way to constrain pulsar masses, need the inclination from light curve modeling, the companion's velocity from spectroscopy modeling, and Icarus should help us provide this super precisely and get nice precise pulsar masses. And if this works and we can get it running a bit quicker, we'll look to create a pipeline basically for any given spider that has a bit of photometry and a bit of spectroscopy, send them into Icarus, and we'll get a nice precise pulsar mass out. Thank you.
Right, so my question is that, so you're getting something there like 3.5, but we know that cannot be right, because you're above the causality limit for Newton stability, which is around 3 solar masses.
Yes.
And also we saw from Colin's written paper on measurement inclination angles. I mean, you see gamma ray eclipses in systems showing that, for instance, for the first black widow system, I mean, there is the estimate from these methods of 2.4, and we see it's actually 1.8.
Yeah.
So my question then has to do, so there's something amiss in the model. So
yeah, this isn't supposed to. This isn't me saying, hey, look, it's 3.5 solar masses. This is me saying this model's missing a lot, and there's a lot to do. So, for example, 1810's got a really asymmetrical light curve, which we can account for in Icarus using convection, moving heat across the surface.
Right, isn't my question. So so I guess you have to really deal with the weather. On the companion.
And so this is a direct heating model, which is why it's probably not great. We have tried, so Romani's paper really focuses on hotspot models, which they have a physical basis for, which is wrong. Pinch binary shock in spider companions, they think that in spider companions, in spider systems. They reckon that you can funnel charged particles down onto specific spots on the star and get hotspots, which then cause this light curve asymmetry. We can account for this in Icarus, but it's not like a physical basis. It's not like we have physics that tells us, oh, look, these particles are going to channel down here. We can just put a spot where we want it, or where the model ends up wanting it, and use that to fit to the asymmetry and then go, okay, how might this spot end up occurring on the star?
We have significant heat transport by, regular winds.
Yeah, so we focus on the hotspot model for 1810 because it's the Romani paper really focuses on hotspots. So I want to try and reproduce their models first. But we also have diffusion, which just helps. So the direct heating model just inputs heat onto the surface element where it lands. It doesn't really move. Diffusion then allows a bit of movement from that individual surface element, and then convective wind models give us some parameters that can then push the heat from one side to the other, depending on which way the asymmetry goes. So that is something that is going to be applied to 1810. And in the previous models I did on this, it does bring the pulsar mass down somewhat, but still like 2.5 or something, so quite big.
I was wondering why spider systems harbor more massive neutrons.
That's a question I should definitely know a better answer to than I do. I have no idea. I really have no idea.
possibility, I mean, the pulsars themselves spin a lot faster, so it's possible if that trend is real. It would be possible that they just accrete it more because they spin faster and so on. So it's something about the evolution of the system that would lead to increase the accretion.
So like a longer period of accretion.
However, the paper by falling there doesn't show like a very big difference for the ones where you can measure masses. So you show that the adjunct treatments are achieved, but you don't see a big difference.
There's still, if you look at the well-measured ones, they're still heavier on average than the double neutron stars are, like significantly heavier. They tend to cluster more like 1.678 solar masses rather than 1.2 or 3 double neutron stars. Some of it could be biases because our models are incomplete. But as Paul says, they spin faster, so they might have accreted more.